Professor Mikhail Tretyakov, from School of Mathematics, University of Nottingham, with the talk Geometric Integrators for Confined Langevin Dynamics. Please.
Thank you, Andrea, for the invitation. It's really a great honor to have this possibility to give a talk at your department with rich and long history in development of stochastic analysis. The talk is based on a joint paper with Malliavin and Takas Sharma, and it is about numerical approximation of confined Langevin dynamics. By the words Langevin dynamics, what is understood here, what is also labeled as underdamped Langevin dynamics or kinetic Langevin dynamics, and which can be described in words that this is a deterministic Hamiltonian dynamics for position and momentum, to which appropriately Wiener noise and friction are added. The word confined here corresponds to the fact that we will be considering those equations in bounded domains with elastic reflection of position from the boundary. Geometric integrators, this term originated from deterministic numerical analysis, and the meaning of that is that the corresponding numerical approximations, they preserve some structural properties of the continuous dynamics. I will start with motivation, saying why we are interested in this object, and then keeping in mind the breadth and depth of this seminar, and also those who attend the seminar. I will put a little bit this talk in the broader context of stochastic numerics, and this will be the next 2 bullet points. And then I will describe the object we are looking at, very briefly link it to the usual reflected stochastic differential equations, and then we will turn our attention to constructing numerical methods. I will show some theoretical results, and depending on time, we'll arrive eventually at numerical experiments, but most likely I will not have time to show them. In terms of motivation, the key question we are trying to answer is how to use stochastic differential equations for sampling from distributions with compact support. Stochastic differential equations such as underdamped Langevin equations, overdamped, they are very broadly used now for sampling from distributions supported on the whole Euclidean space, with applications to Bayesian statistics and molecular dynamics. And it's natural to ask this question when we have those distributions defined on a bounded domain within the Euclidean space. Other applications naturally come from molecular dynamics, because Langevin equations, they are the workforce for molecular dynamic simulations, and it is of interest in molecular dynamics not only consider particles in the whole Euclidean space, but also contain them to some domain. And elastic collisions, they are very natural in terms of physics of movement of particles. As usual, since we have stochastic differential equations, we can view them as stochastic characteristics for some partial differential equations. And indeed, in this case, via the Feynman-Katz formula, we can link these confined Langevin equations with linear parabolic PDEs with specular boundary condition. So now this kind of reminder or link to stochastic numerics, and I put here a generic stochastic differential equation, d-dimensional, where coefficients are sufficiently good. And we can ask a question how to simulate the stochastic differential equation on a computer, say on a fixed interval from t0 to t capital. For that purpose, we can discretize the interval in fixed time steps h. And then on that grid, which we will obtain from the discretization, we can freeze the coefficients at those points on the grid. If you do that, we arrive at the simplest approximation, which is known as the early method. This method is constructive, and I will use this word constructive several times. What I mean by that I can take this object and put it on a computer virtually as it is written. And it also means that the random variables involved are cheap to simulate or simple to simulate. And obviously in the earliest method, we have just Gaussian random variables, and we have very fast random number generators on the computer. Mariama, quite a long time ago now, proved mean-square convergence of this method, and then Gichman and Skorokhod proved its order of accuracy, which is square root of h. When we are talking about numerical approximations, we need to be able to say how accurate the method is. So just convergence in its own right is not sufficient for numerical purposes. And first of all, we look at convergence, how fast the error decays when we decrease the time step. And obviously, there is also a cost associated with computations. And in the case of early method, we compute all coefficients once. And we again, just to remind, we simulate this very simple random variables which we have. What turns out in the case of general stochastic differential equations, where by general I mean that we are not imposing any particular structure on the diffusion coefficient, that there is no higher order mean-square approximations which are constructive. In 1974, Milstein proposed the method which is known as Milstein method, which is of mean-square order 1, but the level of this complexity is I would say considerably higher than the earlier method, because to realize this method, we need to simulate simultaneously from joint distribution of Wiener increments and Lévy areas. Theoretically, it's possible to implement, but that's quite expensive. Then we can start thinking when in practice we need mean-square methods which ensure this closeness of the approximation, this Markov chain, and continuous trajectories of the SD. This is typically the case when one would like to observe or visualize trajectories of a stochastic dynamical system. This appears within nonlinear filtering setting in some very recent optimization algorithms which use stochastic differential equations, and in a very small number of other applications. In practice, we usually need to compute expectations. If you think of statistical applications in molecular dynamics and finance and so on, we would like to compute expectations. And for that reason, we can then require less from numerical methods. We can require that that an expectation of some function of our approximate solution is close to the corresponding exact expectation. And we arrive then at the notion of weak sense convergence, and P is the order of that convergence. I should say, pay attention here that the K, the constant K here, typically depends on F. We are not trying to find constants which are uniform in some class of F. And the natural class of functions, by obvious reasons, is the functions of polynomial growth at infinity. So it's obvious from SD perspective, but also if you think in terms of the use of methods, if you have some stochastic system, you at least would like to simulate variance and other moments.
Excuse me, can I have a question?
Yes, of course.
Here in this definition, do you fix P and then look for such estimation, or you just want to have such estimation for any function of polynomial growth? maybe with different p. Does it depend on degree of polynomial, for example?
So let me answer slightly differently. So our aim is to derive x bar such that this inequality holds. And the degree of polynomial would be dictated whether such moments exist for SD. But k, the constant k, will depend on a particular polynomial, but not p, not the order.
I see. So it looks like it is very close to Wasserstein distance between distributions of xt and x bar t. Yeah.
It's close, but not at the same time, because in Wasserstein we are taking sub over some class of functions. We are not doing that here. That k depends on
Yeah,
functions.
it was actually the reason of my question. Okay, thank you very much.
So you will see later that I will require more from test functions, that they are, for instance, sufficiently smooth. But there are ways to remove smoothness in certain circumstances.
Okay.
So why we are looking at weak convergence at all? Obviously, from mean square, we will get weak convergence. The reason for that, that we can construct simpler methods and with high order of convergence. So if you look at the earlier method we have on the previous slide, which in mean square has convergence with order 1/2, in this weak sense, it has convergence of order 1. And moreover, we can, instead of Gaussian, takes plus minus 1 with probability 1/2, and this Markov chain will also converge in a weak sense with order 1. But what is again more important, that I can obtain constructive numerical methods, say of order 2 in this weak sense convergence, which is difficult in the constructive way to get in the mean square sense. And all the methods we are constructing, these weak schemes, we call them, the random variables we use in those schemes, they are either just Gaussians or discrete random variables, so again, very simple to simulate. So we have this mixture of complexity, accuracy, and then applications which dictates the setup. I also should mention that when we simulate expectations on a computer, we need to do another approximation. So we need to come up with statistical estimator for expectations, say this the simplest one. And then the number, this U bar, which we'll have on a computer, has two errors. One is statistical error, also called the Monte Carlo error, and the other, the error of numerical integration. In this talk, I will only be concerned with the error of numerical integration. I will ignore the other error. Before I go to Langevin equations in bounded domains, let me say a few words about Langevin equations in the whole Euclidean space. What we have on the screen is the simplest and the most used Langevin equations within molecular dynamics and statistics, and also now within optimization setting. You see that if I put gamma equal to 0, then I have just Hamiltonian system with separable Hamiltonian. So my U is a potential minus gradient U is a force. We have friction here. I also can write it down formally on a physical level as a system of second order differential equations. Further, under appropriate conditions on the potential U, solution to the system is ergodic, and its density is of this form. So it's a Gibbs invariant measure. We can look from practical angle on this measure from two sides. If you are talking about molecular dynamics, then this will be interacting potential between particles. But if you look from the statistical angle, then we might be given a density from which we'd like to sample. And then we can do the reverse exercise from this density, construct U, and plug in here. Since this system is ergodic with this density, if we simulate it over a long period of time, then we will come close to the stationary regime and we can start sampling. So that's the idea of using SDs within the context of sampling from given distributions. Again, from practical angle, what the problem here is that it's all very multidimensional. So we are talking about dimension of Q being 100, 1,000, or 100,000 if you are talking about molecular dynamics. And we need to simulate the system over a long period of time, and then this ideas of geometric integration comes into play because it's useful to preserve certain structural properties within the dynamics. In terms of the error estimates we had in the definition, different methods has different constants in front of HP, and they may depend differently on time, and usually geometric integrators are better in that respect. In terms of constructing numerical methods for Langevin equations, to get these geometric integrators, one typically use the splitting technique, which again comes from deterministic numerical analysis, where you take the flow of your differential equation and start splitting in parts, each of which you can solve exactly. In the case of Langevin equations, we can split it in Einstein-Uhlenbeck, so we can solve exactly. Then we propagate the position with constant momentum. So again, we can solve exactly. And finally, we kick the momentum at a fixed position Q. We have three exact solutions here. We concatenate them, and we get approximation of our SD. And obviously, we can have a lot of different concatenations arriving at different methods. All this has been studied, and there are still quite a lot of papers appearing in terms of properties of the methods, their structural properties, convergence, ergodicity, and so on. What we will be talking for the remaining part of the presentation is about confined Langevin dynamics. I'm writing here, it's a little bit more general form. As the Langevin dynamics, I have this coefficient B depending on P and Q, but we will come to a simpler form in a couple of slides too. If I don't have this red term, then this is just Langevin type dynamics living in the whole Euclidean space. What this red term does, this Cadillac process does, added to the momentum, that it leads to the fact that Q, the position, remains in a bounded domain G with boundary partial G, and G will be outward normal vector at the boundary. I would say from the beginning that we will assume that boundary is nice, that it is sufficiently smooth. So we are not looking here at pathological cases. If you look at the structure of that term, you will see that what it does at the time when Q hits the boundary, it preserves the tangential part of P, but reverses the orthogonal part of P, orthogonal to the boundary. I have a little bit more explanations on the next slide. What I would like also to say here, that this object looks like not particularly well studied because there are very limited number of papers in comparison, say, with usual Langevin dynamics. So I write this term here in this form where tau i's are collisions of Q with the boundary, and you see that we project P on the normal and then multiply by normal, and it's factor 2, which leads to the elastic collision. Elastic collision also, we can visualize that, say we play billiard, and if it's ideal billiard, then we hit the ball over the edge of billiard, it comes at an angle, say alpha, and it goes back at the same but opposite alpha from the wall, and no energy is lost when the collision happens. So on this slide, effectively, this sentence, which is at the second sentence, explains what happened in that T acts on the momentum to reverse the direction of the orthogonal component, keeping tangential component unchanged. We also looked at the simplified version of the equation we have on the previous slide, where the drift is force minus friction, as we had at the beginning a couple of slides ago when I showed the standard Langevin dynamics, and under appropriate assumptions on U, say U is smooth, boundary is smooth, solution to this SD is ergodic, with invariant measure, it again takes Gibbs form. However, Z here depends on the domain. So the geometry is hidden in normalization constant, and if you think, say, of a picture of density in the whole space and picture in a bounded domain, they are quite different. Now, a quick comment about reflected stochastic differential equation. So here we are looking at Skorokhod problem. The solution is, as usual, X and L. And we have again here the force. Under the same conditions, a solution to this SD is ergodic with Gibbs invariant measure. And this obviously density coincides with the marginal for the Langevin equation we had on the previous slide. So this object also can be used for the same purpose of sampling from distributions with compact support, and that we explored it with Ben and Akash in our previous paper. Also, I would like to pay attention that this red term R, which is responsible for reflection in the case of Langevin dynamics, it's fully determined by P and Q. So the solution there is just P and Q. So before we go to more formulas, let me show you some short videos. So the first one is a trajectory of reflected SD in a disk, and you see that we have reflection always along the normal to the boundary. Trajectory is rough, as it should be, because we have inner process in both components, and here we use the method which we developed with Ben and Akash in the previous paper. Now we have on the next short movie, we have a trajectory in terms of Q, only position of CLD. I wrote here that CLD is two-dimensional, meaning that it has two degrees of freedom. So we have two-dimensional position and two-dimensional momentum. A reflection goes at the same angle, so that's what we discussed. And also you can see that trajectory is relatively smooth because Q doesn't have Wiener process, so it is differential. What is probably more interesting is the next video, which relates to 1 degree of freedom. And here I can plot then the phase portrait. On the x-axis, we'll have position Q. On the y-axis, we will have momentum P. And the domain is a semi-line with boundary at minus 1. When our Q hits the boundary, then the momentum appears at the other side. Here, obviously, because it is one-dimensional, there is no tangential part. So it's the momentum essentially changing sign from minus to plus when collision happens. And as you would expect, the momentum is discontinuous at the time of collision of particles with the boundary. We can write down the backward Kolmogorov equation in the usual way. And since we are working with SDs in bounded domain, then we have to prescribe a boundary condition. On this occasion, this is the specular boundary condition, which obviously resembles what happens when trajectories hit the boundary. And we link this in the usual way via Feynman-Katz formula, where Q and P solves our CLD object. Similarly to confined Langevin dynamics, there is also very, very little literature on PDEs with specular boundary condition in comparison, say, with PDEs with Neumann, Dirichlet, Robin, where everything has been studied in terms of spaces, classes, and so on. It looks like PDE community just started to look at that object and establishing its properties. We need quite a few assumptions, and these assumptions are aimed for us to get first-order convergence. They are sufficient assumptions. So we require that boundary is C4. I should pay attention that we do not require that G is convex, that B is C2 and grows not faster than linearly in P. Test functions are C for 4. And we also need to put assumption on the solution to the backward Kolmogorov equation. And what I cite here is a very recent paper where they study equations of boundary value problems of that type. In the case of ECLD, when we have this ergodic behavior, we assume that potential is smooth. Greater than 1 is just very technical assumption. It's not really important because in the equation itself we have gradient. And under this assumption, one may prove that solution is exponentially ergodic. And what we will be interested in is computing this phi bar, which is average with respect of phi with respect to the invariant measure of the ECLD. We can write down Fokker-Planck equation, stationary Fokker-Planck equation with specular boundary condition, and it's straightforward to check that Gibbs density, which we saw before, satisfies the stationary Fokker-Planck equation, and thanks to p square appearing here, to the symmetry, it satisfies the boundary condition too. For proving convergence in terms of this ergodic limit, we need an extra assumption on the backward Kolmogorov equation that its derivatives decay exponentially with time, which is a natural assumption. So now we are coming to construction of numerical methods. We have a uniform time discretization. H is time step, and I'm just recalling the object we would like to discretize. When we consider stochastic differential equations in bounded domains and would like to approximate them, then we have, physically speaking, two regimes. We have when our approximating Markov chain is sort of far from the boundary, when it doesn't really feel the boundary, or I will say it is inside the domain. For those states, we can use more or less any method from stochastic numerics for SDEs in a whole Euclidean space. But when our approximated Markov chain comes closer to the boundary, we need to do something about it. And then this builds in an additional construction in the numerical method with sort of if operation inside. Since this is critical, this is the starting point for us to construct numerical methods. So what we have on this slide is an element of one step within approximation, within constructing of Markov chain, moving from one state to another, and this is kind of sub-step. We assume that currently we are at QP. And then what we do, we check whether we need to do something about that belief in the bounded domain or not. And we do it in the following manner, that we propagate our position with the momentum, with fixed momentum P, over this time interval H. And if the new position of the particle, the new position of the particle is inside the domain, then this is a good position. We take it and work with it further. But if it leaves, we need to do something about it because the continuous trajectories do not leave. And what we do here, what I want to try to do is to switch to, yeah, I think it worked, like just to show in a picture what we do, and then you will see in formulas. So we have a boundary, so this is my domain G going that direction. I start somewhere here with Q, then I propagate it, and I arrive at Q plus pH. So I cross the boundary, I'm outside. Next, I'm finding QC, which is Q plus minimum tau. So here, obviously, tau unique, but it might be not. That's all this point on the line. And next, what we do in the numerical algorithm, so we have this angle alpha here, and we reflect back with the same angle alpha, and we are getting Q1, which is QC plus remaining time interval multiplied by P1. And this P1 relates to P small with which we started, so that the tangential parts are the same, while the orthogonal component is opposite in P1 to P. So basically, we are implementing in this discrete manner what happens to the continuous trajectories on the boundary. So let me switch back to 2 slides. And here, just written in terms of formulas, we find QC, P1, and Q1. The tau which we have here depends on Q and P and on the boundary. So if I fix QP, then tau is not random. But over the course of development of the Markov chain, tau obviously becomes random. Now we need to combine this with approximating the other bits of Langevin equation, and we do so by approximating the B's and the Wiener process just using the Euler scheme. And this C, we can think that this is Gaussian random variable with 0 mean at unit and unit variance. This I will now concatenate with the collision step. So we are using these ideas of splitting, and we have 2 conjugate schemes. In the first one, we first do the Euler step, this delta for B and Wiener process, and then we do the collision step. In the other one, we do the other way around. Both of them require just one evaluation of force per step or one evaluation of B per step. And if we would not have a collision, then this last line will be just QK plus 1 equal to QK plus H multiplied by P hat, and that's in an Euler type scheme, which has first order weak convergence. But then we would be living in the whole Euclidean space. These 2 methods and all other methods we developed in our paper, they all preserve momenta at the collision, as the continuous dynamics does. Numerical methods which were derived before us do not have this property, and this property we do use in some of our proofs. So it looks simple, but we have a problem. We have a problem that due to curvature of the domain, we can have multi-collisions in a single step. In comparison with other methods, we will not have, this method developed before us, we will not have multi-collisions in the case of half space by the design of the method. But when domain is curved, then geometry starts playing its role. Just to illustrate what I mean by multi-collision and how it occurs, we have this picture. So we start with this Q, and we are sort of very close to a grazing set. We have a large value of momentum, and the angle is very small. So we will shoot originally very far, then we find this QC, and if I would follow what we had as an AC, my next Q should be inside. But it's not difficult to imagine that I can create situation like in the picture that it is outside. And then if I repeat it many times, then eventually I should be inside the domain. Obviously here it's in a way pathological example because my time step is large and so on. So in practice, I would take small time steps so that this occurrence would be rare, but still they can happen. And we see multi-collisions in numerical experiments for moderate time steps. For small time steps, we don't see. This collision dynamics is deterministic, as we discussed before, and it is essentially the same or very close to Billiard theory. And it complicates the proofs we have done because we need some kind of estimates in a certain way of how many collisions we can have inside the step. So this result is present in the paper, but I didn't formulate it for the slides. Algorithmically, there is an easy fix. We just repeat this AC step many times until we are back to the domain. What we proved are the following theorems. So for the system, the more general Langevin type equation, we prove convergence with weak order 1. And C here can depend on integration time. So we are proving this on a finite time interval. And for this ergodic CLD, we also prove convergence with first order, but we have this correction which is naturally coming from geometric ergodicity. And you see that here we approximate this ergodic limit with respect to the invariant measure, and we approximate it by what is called ensemble averaging. The constant C here doesn't depend on time. The proofs of both lemmas follow the same path, just the second, these theorems follow the same path, just the second theorem needs an extra care of monitoring dependence of constants on time. So the proof is based on 3 lemmas. First, we need to prove that that moments of P are bounded, obviously moments of Q are bounded because we have bounded domain. And this follows from the fact that we have linear growth of this B, and in the case of ECLD, we have minus P in the equation for the momentum. Next, we need to prove what is known as one-step error lemma or local error lemma, where we look at how much error is generated at a single step of our Markov chain. And the error is measured through the backward Kolmogorov equation. The meaning in terms of overall global convergence of this local error is that the global error is essentially equal to the sum of those local errors. So when we prove global convergence, we appropriately write a telescopic sum, and then we have a sum of local errors. In the numerical method, we have 2 parts. One, that we walk sort of inside the domain, and we use Euler method, and as expected, we have here local error in weak sense h square, which gives us first order for Euler schemes in terms of global error in the Euclidean case. So that's a consistent part of the error, and the other part is related to us doing this reflected step. And you see that we have h here. If you just start summing those local errors over the number of steps, and then the number of steps is proportional to 1 over h, we will not get a convergence. So we need a more accurate estimate for this expectation. Lemma 5 is proved using tedious Taylor expansions and backward Kolmogorov equation. So that's what is used there.
Michael,
yes.
may I ask a question?
Yes.
You have M on the right-hand side of M side, but you don't have M on the left-hand side. So why don't you take M is 1?
Sorry?
what is n in the right-hand side of lemma 5?
You mean this bit?
Yeah, p to the power 2n. Oh, there is no n in the left-hand side.
You mean this one?
No,
No,
the
M.
expectation of u minus u.
M is a power. So we have this functions phi, which can have polynomial growth in P. And then it translates to the fact that solution of the Kolmogorov equation can grow. And that's why, Andrei, we need also this lemma with some M. But we are not specifying, so this M, whatever comes from the calculations and from the Kolmogorov equation, and it depends on this function phi. So we need to prove this lemma, and if I kind of forget that I have this bracket, this long bracket here, which just comes from this Taylor expansion, we have to have it. But what I'm summing here on the physical level of thinking, I'm summing just indicator functions that my Markov chain left the domain. So what I have here is average number of steps which went out of the domain, where this reflection step was required. And it turns out that this average number of steps is bounded by a constant which doesn't depend on the time step. And thanks to this fact, then when we are summing, we are just getting some constant out of that, but the order stays as order 1. And lemma of this type is usually critical in more or less any setting when we solve SDs in bounded domains, because usually it's quite difficult to have an effective constructive approximation near the boundary. The proof of this lemma is based on the following trick that we introduce the boundary value problem associated with the Markov chain. So this T blackboard bolt is the transition operator, and this problem has an analytical solution. So we can write it in this form, and if you compare what we have here, it's sort of very similar expression. And then if I can find V, which I would normally call a Lyapunov or Lyapunov type function, so that it solves with some G this problem, and this G satisfies this inequality, where on the right-hand side we have exactly what we have in the lemma, then V small, which is the expression in the lemma, is bounded by V capital, and V capital I construct it such that it doesn't bring out H. And just for fun, I show what kind of construction of this V we ended up with, and after that, a few pages of routine calculations to show that this V gives us a G of the right type. So I'm not showing this on slides. Now I'd like to spend a bit of time on second order schemes, which we derived for this ECLD model, where we have force and friction. We need a bit more random variables there, but again, we can just assume that all of them are Gaussian with zero mean and unit variance. On the next slide, O big will denote a solution for the Einstein-Uhlenbeck SDE we had at the very beginning of the talk, or time step H. So we are using now the splitting ideas, which I tried to illustrate for the Euclidean case at the beginning. And for instance, we can write the following three schemes. There are other three schemes which we also used in the experiments, and in principle, these concatenations, I think, can introduce 9 schemes. Let us look at one of them on this left-right corner. We first do Einstein-Uhlenbeck on a half step, then we kick the momentum on a half step at a fixed position. After that, we do our reflection step over the whole H. And then we symmetrically do kick of the momentum and Einstein-Uhlenbeck step. So it is a symmetric scheme. The other, if you have a glance on those, they're just different concatenations of exactly the same idea. For this scheme, we can look at two limiting cases. One limiting case is that I do not have boundary. So it's I'm looking at Langevin equations in the whole domain. Then this method is very well known, and what we'll have in the middle, it will be just qk plus 1 equal to qk h plus h multiplied by this p hat. And in the whole Euclidean space, it's very well known, tested, theoretically known, and so on, that this method is of second order. Now, the next limiting case we can look at is to put this gamma equal to 0. So if I put gamma equal to 0, I'm getting a deterministic Hamiltonian system with reflection at the boundary. In that case, of course, I do not have Einstein-Uhlenbeck, so they are gone. I have just these three things. And this method does exist in deterministic literature exactly with this AC we constructed, but this method is of first order. And here we came to quite a large contradiction when we start working on that, because in the stochastic numerics, the convention or untold, unwritten convention is that if I take a deterministic method for deterministic ODE and appropriately generalize it to a stochastic setting, then the order can't increase. And obviously, any stochastic method, you can look from the other angle that any stochastic method, when we switch off the noise, becoming method for the corresponding ODE. And again, convention was that stochastic method can't have higher order than the deterministic. Here, by some initially look like miraculous calculations, we arrived that this method in the stochastic case is actually second order. And that's what I will try to talk a little bit about. So we showed it in terms of justification for the case when domain is half space and it is oriented so that the boundary is when the first position is equal to 0, then the tau, this collision time, I can compute analytically, no kind of curvature playing or geometry playing a role. And we proved lemma of this, one-step lemma of this type. And the proof works because of this sentence at the end, that an average collision time is equal to 1/2 up to terms of order h squared. So let me kind of skip a lot of calculations and just show this, this slide. If you do this accurate Taylor expansion of the local error, one-step error, and we track everything, then eventually we arrive at the following expression. R1 and R2 can be ignored, they're already sufficiently small. But you see here these red brackets, that if tau is exactly at h12, those terms are killed. So essentially, if my collision is symmetric, I'm getting an order. If one think of deterministic Hamiltonian dynamics in some bounded domain with some curvature, this never would happen. So my tau never would be h12. The same, obviously, in stochastic case, my tau is random. But it turns out that expectation in some form of this tau is equal to h12 plus term of higher order. And that explains why in experiments we saw second order convergence. So I think I will stop at that, allowing time for questions. So I'll skip experiments and go just to the page with conclusions. Thank you.
Thank you very much. And maybe someone have questions or comments, please.
I have a question. So, in our model, we have this Brownian motion term, sigma times w. Do we get some sensible physical model if we instead put a integral there? So, generalize this setting. And, is this still mathematically tractable?
Okay, so if we do it in the case of usual Langevin dynamics, I mean in the whole Euclidean space. So this object is studied and we can do numerical methods for this as well. So this is sometimes useful because you can, so let me go to the beginning so that will be clearer what I say. So here in the setting of sampling from a given distribution, we have freedom. We have uncountable number of possibilities how to design a stochastic or random system which will have this invariant measure. And this includes this object, and we indeed can put here some sigma depending on, let's say, Q. Then we will need to have a correction appropriate so that we are still sampling from that distribution. And there are some benefits of that because the convergence to ergodic limits depends on the spectral gap, and you might want to choose here sigma so that a spectral gap is bigger so that convergence is faster. However, in the case of Langevin dynamics in bounded domains, there is no proof of existence uniqueness apart from one-dimensional case. So that's why we sort of didn't consider this. But in principle, this object can be defined. But then there is a need to prove that existence and uniqueness of the strong solution for those objects.
Very interesting, thank you.
Okay. Other questions, please? I have a few questions. First one is what about the following approach? You mentioned it slightly, but it looks like it can work at least for usual stochastic differential equation when we consider it with reflection on the half plane. One can proceed as follows. Let us do usual approximation like in Euler-Maruyama scheme. Then we know convergence. Then apply a procedure which comes from Skorokhod problem and apply it to the difference approximation. Then we get the answer, and I think that the accuracy will not change.
Yeah, so probably you'll get the same order of convergence we have. So this is not exactly Skorokhod setting, right? Because we have well, the classical Skorokhod problem setting because we have elastic collision we jump out of the domain. So first, when it is one-dimensional or when it is half plane, there are more things which can be potentially done because you can compute exit times, for instance, right? So so there are more flexibility when it is half space. So we have not looked at that to derive specific methods for half space. When it is curved, it's becoming a little bit different in terms of finding the solution. And also when you will be finding effectively Skorokhod map in that, it will be in discrete manner. So your continuous trajectory will be doing something else during this time. And then error will be introduced because time is going on while in Markov chain, we just observe it at a fixed instances, right? So then, say, I mean, if you start approximating trajectory, it's not like we just matching essentially generators, that's all what we do here, then you can imagine that within your Markov chain, you missed the point when the exact trajectory went out.
Oh yes, but why we are so careful about it? Let it came out for small times and go back. Why not? Yeah, we will still if the procedure which give us the reflected solution from non-reflected is in some sense keeping the accuracy of approximation, it looks like we can give this we can continue with this approximation. Yeah.
Yes, but in a way, what we constructed here, we're doing similar because the reflection step itself just mimics the continuous dynamics.
Mhm.
So
Yeah, it is very close. It was just the thought which was useful in one-dimensional case. So I will be glad to see that it works also in multi-dimensional. Yeah.
So I probably can say, because obviously you worked a lot on reflected SDs and your group, that for reflected SDs, I mean the usual Skorokhod problem, there are, if you think about mean square approximation, there is either penalty method. So when you introduce penalty if you go outside, penalty related to the distance. So then
Yeah.
your scheme is defined everywhere, but if you jump a little bit out, you have a strong penalty which brings you back.
Yeah.
Or you do projection
Mhm.
on the boundary. In the weak sense, we used kind of kicking back inside the domain, but it was in weak sense again, much in the generators. But this is in general domains. When it is one-dimensional or flat, there is this paper written in 90s by Lippengler where he just uses
Yes,
exact solution.
Dominique Lepinho, yeah.
Yes, and he did exactly what you said, because in that situations you can solve the Skorokhod problem exactly. But as soon as your domain curved, that became. I don't know whether I answered the question or not.
Thank you very much. And also, I have to mention that in the beginning you told about the accuracy of approximation in the initial Euler scheme for ordinary stochastic differential equation. And I must say that in the book of Kuznetsov, I think there is some idea how to improve the rate of convergence in square mean just using the approximation simulation, not only the V area, as you said, but even higher multiple integrals. We can substitute it by Hermite polynomials. Yeah.
Yes,
So,
that's correct. So theoretically, on paper, derivation of mean square methods is just iterating iter formula. You can get whatever order you would like. But then you have this problem of simulating of iterative integrals. Yes, they can be done using Fourier, they can be done using various type of polynomials, including Hermite, but the cost goes up because you need to do those. What I saw recently that people start using, say, neural network, which would work as a random generator for Levy areas. So that could be fast. But you need kind of more complicated random variables. And then, yes, there is a whole kind of industry in terms of how to approximately sample from that joint distribution. Exactly, because the higher you go, the more iterative integrals you are getting, and you need to sample from this joint distribution because here it is effectively pathwise convergence.
Okay, thank you very much. Thank you again for very interesting talk. especially in my case, because now I have PhD student, our secretary of seminar, Katerina Kustareva, who study numerical approximation to stochastic differential equation with interaction. So I think it was extremely useful. Thank you very much. For today, we finish our job. And Katerina, do you know who will be the next speaker?
Sure, the next speaker will be Alexei Galganov.
Okay. Then for today, that's all. Thanks everybody, and bye. See you next week. Bye.
Thanks a lot, Andrei.
Thank you so much. Bye.
Bye.